Grocery shopping can be tedious, dull, arduous to say the least, but what if going to the supermarket could be an exciting, interactive experience? Imagine walking through the produce section of your local supermarket. You pick up a pineapple and think to yourself, why do I even need this? What will I ever do with it? You put it back on the pile of pineapples you took it from and walk away. This is a common situation in the produce section. While other areas of stores are able to advertise products through colorful packaging, fun fonts, and small plastic prizes and cereal boxes, we've all fallen for it. The produce section is really just filled with produce. To keep the fresh foods up to speed with the rest of the store, something has to happen to fix the monotonous fruit and vegetable experience of your average grocery store. Let's go back to the situation we talked about before. Instead of putting back the pineapple, you can walk up to a nearby screen, hold the pineapple up to a built-in webcam, and the software of the screen gives you recipes, reviews, and videos about that pineapple. You would feel more excited about the prospect of buying this pineapple and have ideas in your head about the many things you can cook and bake with it. Powered by artificial intelligence, the future of in-person grocery shopping is in interactive elements such as image recognition and other forms of computer vision, as well as on-demand information about items. Believe it or not, this is not sci-fi. It's very close to becoming a reality. 66% of consumers say that interactive store technology could lead them to choose one store over another. Additionally, 61% of omni-channel shoppers, people who shop both online and in-store, have walked out of stores because of lack of interest in tech amenities. Turning the produce section into a tech playground is ideal for retaining these customers and encouraging them to buy more healthy foods. But how exactly does one achieve this? Screens are a simple way to bring technology into any environment. Consumers are already familiar with how to use them since over 91% of the world's population has a mobile phone. But the trick is making the screens different to the technology we all know and love, and this is where artificial intelligence comes in. A grocery store screen would comprise of three basic components: a touchscreen, a webcam, as well as software built to leverage the screen and webcam to gather and display useful information. First of all, the touchscreen would display an interface the user can use to take a picture of their produce item. A live webcam feed will be shown, along with a button that allows them to capture a frame of that webcam feed to pass into the AI model. The AI model would classify what kind of produce item is in the picture. The touchscreen would then display information about the produce item detected in the image and give the user recipe ideas on how they can use this food in their daily cooking. The AI within a grocery screen would rely on a computer vision technique called a convolutional neural network, or CNN for short. CNNs are computer vision algorithms used primarily for image classification and other 2D image-related tasks, but they are flexible enough to be used for other types of tasks as well. I built my own prototype of the CNN that could be used in a grocery store setting, and I'm going to show you how it works. The particular CNN that I use within this project is a slight variation of AlexNet. However, I use something called batch normalization multiple times throughout the model's structure, rather than performing mean and standard deviation normalization of the entire dataset within the data transforms. Normalization is when all pixel values of an image are put between 0 and 1, creating an image that is optimal for feeding through a neural network. In my program, instead of normalizing the entire dataset at the beginning of the program, I normalize each individual batch of images multiple times throughout the training process. The model was trained to classify images from a dataset called Fruits 360, which is a dataset comprised of 90,000 images of fruits and vegetables on a controlled background. Initially, I attempted to train the model on a different dataset. This dataset was smaller, only about 10,000 images. The model seemed to struggle with the chaotic environment the photos were captured on. This dataset did not give me the accuracy I needed. It continually classified every example I fed it as a potato. As soon as I changed the dataset to Fruits 360, the accuracy went up significantly, from about 33% up to 99.6%. So let's dig into that code. I started out by importing all of the Python libraries I would need. A Python library is a quick and easy way to import tools and functions that you need in a project. For example, importing the time module gives you access to tools allowing you to time certain aspects of a program. This project used PyTorch, a machine learning library, to build and train the neural network. Torch Vision is a library used for computer vision within PyTorch, in other words, for processing and learning patterns within images. PIL is a library used for managing image data with Python. NumPy is used when I want to turn images into NumPy arrays, and Matplotlib is used to show visualizations and graph data. I also cloned my GitHub repository with all of my data and various models I trained within it. One of the first things I always do in my machine learning projects is define hyperparameters. Essentially, by storing values such as the number of images per batch or the learning rate of the model within variables, they can be easily referenced and changed to fine-tune the model later on. The next thing I did was create lists of transforms that would be applied to the data I feed into the model. For my training data, I wanted to augment it to make it harder for the model to learn. Training a neural network is a bit like studying for a math test. If you practice the hardest questions before the test, the medium difficulty questions that are on the test will be a breeze for you to solve. It's the same for a neural network. If you feed it images that are augmented or changed subtly to make them harder to recognize, it will perform better on easier data it has never seen before. By setting up random horizontal and vertical flips, the classifier will be able to recognize produce items regardless of orientation. When looking at these data transforms on the screen, you can see that I use random horizontal flip with a probability of 30%, random vertical flip with a probability of 10%, and 2Tensor. 2Tensor allows the input image to be fed into a PyTorch-defined neural network, as PyTorch is created for the explicit purpose of working with tensor data. Test transforms include resizing input to 100 pixels by 100 pixels, as when I was testing the model after I'd finished, it seemed that the original test input was not this size. When I was building the model, I originally had many more transforms within the training transforms. A significant transform that I included was color jitter, which tweaks the colors within the image slightly. It turns out that I was augmenting the image too much, as it wasn't learning to recognize the fruits correctly, and it was confusing their colors. A lesson I learned from building this model was to only use transforms you actually need, as changing too much can end up confusing the model. Next, I defined my datasets. The training dataset was pulled from Fruits360's training folder, which I accessed via the cloned GitHub repository I mentioned earlier. I then applied the training transforms to this dataset and split it into two sections, one training section and one validation section. Training data is used to teach the model how to perform its job, in this case classifying what kind of fruit is in a picture. Validation data is used to check how well the model performs on data it's never seen before. The importance of validation data is in preventing overfitting. Overfitting is when a model learns to recognize individual images rather than a general pattern. For example, it would learn to recognize one specific apple rather than learning what all apples generally look like. Validation data lets the programmer check that their model performs well on new examples so they can see it's able to generalize. You can see that I used an 80-20 ratio to split my training data into these two subsets, and I created an entirely separate dataset from the test directory for use later on in the program. The next thing I did was set up my data loaders. Data loaders are the way that the computer is able to cycle through the datasets defined before. For example, a dataset would be the words in a book, but the data loader would be the structure of the book itself that allows the reader to flip through the pages in order. Setting this up is pretty straightforward. I used PyTorch's built-in data loader class to define one data loader for each of my datasets. You'll notice that for the train and validation data, the batch size parameter is set to the hyperparameter batch size that I defined earlier. But for the test data, the batch size is 1. This was intentional. When I visualize the data and subsequent predictions later, I want to be able to visualize single images rather than a full batch of data. Now we're getting to the exciting part. Here's where I define my convolutional neural network. This network is based off AlexNet, but you can see the added batch normalization and slightly altered linear layers at the end. AlexNet is also comprised of multiple convolutional layers to isolate feature maps of the fruits, then linear layers at the end to create a class prediction from those feature maps. Finally, before I started training my model, I defined an optimizer and a loss function. For my model, I chose to use SGD. I used the Atom optimizer initially, but found that the model actually performed better with a more basic SGD optimizer. Then I transferred my model and optimizer to the GPU available in Google Colab, which was the environment I was working in. Just a few more functions to go before the training loop, final accuracy calculation being one of them. This function allows for the accuracy of a model to be tested at any point. Using the argmax function, I can get the top prediction outputted from the model, as the model outputs a tensor of probabilities of each class being seen in the input image. Then I can check if it's correct and return a final accuracy. Almost there! Defining a training function is a bit lengthier. It consists of bringing the images and labels to the GPU, passing the images through the model, getting a loss value from the outputs of the model, and back propagating to update the weights of the CNN. This is what makes a training function train. When the weights are updated, the model can perform better on the next round of training, and the improvements stack up. Then an accuracy is calculated based on the predicted and actual labels. The function returns the loss and accuracy of the epoch. Last one, this function allows for evaluation of the model without updating the weights. And this is useful for seeing how accurate the model is on the validation and testing data, as we don't want to update the weights when going through those datasets. Time to train. I started out by importing the time module so I can check how long it takes for each epoch to train. I created lists for each of the datasets, one for loss and one for accuracy. I also set an epoch variable so I could track the number of epochs required to get the desired accuracy. Then I defined a while loop for training. This loop runs until the accuracy on validation data is more than 99.5%. The loop starts out by printing the epoch number, setting a start time, then training the model on training data. It saves the output of the function, which is loss and accuracy, in variables, then takes the time that the epoch finished. It repeats the process for validation, but uses the evaluation function rather than the training one. Remember, we don't want to updating the weights of the model when going through validation data. At the very end, it prints out statistics of the epoch, including the loss, accuracy, and time taken to train and validate. By the end of a loop, a model results that has greater than 99.5% accuracy. Once the model is trained, I did not want all my hard work to go to waste, so I saved my model. The next part was optional, but I decided to have a look at it anyway. I displayed graphs, the loss and accuracy over the number of epochs it took to train. Then I calculated the accuracy percentage of the model on test data, using the evaluation function defined before. Now that I had a working model, I wanted to see some real-world examples of how it performs. To do this, I wrote a function that allowed me to get a prediction of the class of any image from a dataset fed into it. This function starts out by transforming the dataset item to an image and storing that image in a variable. It then performs a few operations on it before getting the prediction of class from the model. The function returns the predicted class number, actual class pulled from the dataset storage, and the image itself. We're coming to the end of the model program. The last thing I did was print out some samples from the dataset along with the predicted and actual classes. Here's the output of that code. You can see all the different images that were fed in, along with the predicted and actual class. As you can see, the model does pretty well overall. Now it's time to implement a prototype of how it could work in a grocery store. I created a sample program which outputs a QR code linking to a set of recipes available for that produce item. This code outputs a QR code that looks something like this. If you scan that, you'll be able to see a list of recipes for apples. A shopper is able to scan this QR code with their phone and read to a curated list of recipes available to use with the classified fruit or vegetable. The customer becomes more motivated to use this produce item and is far more likely to buy the produce item now that they have a perfect image in their head of a delicious meal they're going to cook with it. This solution also encourages healthy eating since the produce section will become the highlight of the store. Here are some mock-ups of how a commercial version of this project could look. Imagine the impact of an engaging grocery shop on the level of enjoyment of your everyday routine. If each day can be made 1% better by a bit of fun at the store, imagine the overall improvement to your life. If you're interested in following along with what I'm up to, feel free to subscribe to my newsletter, connect with me on LinkedIn, follow my Medium, or check out my tks.life profile. See you next time!